a few minutes after that as well. And I have prepared a presentation. Of course, I wish that I could have been IRL, and I was considering flying down for this very important and interesting presentation to, the way I see it, a highly interesting group of people. But that will have to be in a follow-up meeting in the future, and I can come down, and if you're interested in interacting with me and my colleagues over here, I'm sure we can arrange for a visit. What I will do, and in the sake of keeping the quality of my presentation, the interesting stuff is in my slides and in the videos and in the demos that I will show you. And as many of you know, Zoom is a terrible piece of software for showing videos. So I will actually do a little bit of a hack here and turn my camera feed into a video feed for you. The consequence of that is that you are not going to see me as a talking head here. And that's perhaps the benefit of the presentation. So I'll switch over and you will still hear my voice. And so my presentation is called Exploranation, and one of my goals for today is to make you appreciate this new word that we invented over here. My wife, she's upset with me. She's American. She says, you cannot invent new words in English, but I did anyway, because I didn't have a good way of explaining what it is that we mean by exploration. But it's all about creating those bridges between researchers and the general public, and use the visual media to do that. To put you a little bit in the context of how we're doing that, Torsten was very kind to mention the Visualization Center that I have spent almost 25 years of my life building in the city of Norrköping in Sweden. And it's a pretty unique setup in the sense that it contains a very large research unit, about 120 people at this point, who are focused on visualization, graphics, media, but it's embedded in the context of a science center and a museum. So in this laboratory, we have public spaces, we have a dome theater, we have spin-off companies, we have all of these things going on, about 200 people sitting here working in this domain. So, and I think this is a part of the uniqueness that we have, is that we're really shortcutting the distance between very basic research on graphics, visualization, computer science, and the mission to have interesting topics, relevant topics that we communicate using the visual media to about 200,000 visitors per year going through our lab spaces. Just to give you a little bit of a flavor of the research groups that we have, we are doing a lot of fundamental work on computer graphics and image processing. The picture up on the left there actually has a funny story behind it, because it's, you know, that Sweden has a big furniture company called IKEA. And they produce a catalog every year, and they used to have 70 photographers, full-time photographers, to take pictures of furniture. Nowadays they have none, because everything is virtual, and it's based on rendering techniques that we have developed here. So everything is fake in the IKEA catalog. Don't trust anything anymore. We do a lot of work on scientific visualization. You will see a few examples of that. We are looking at the human body, medical things. Immersive visualization, I won't be able to show you much of that since we're not on site, but in our planetarium setup, in our dome theater, we do interactive shows taking you to the end of the universe. We have one in-house group that is very important to us, and that's the group on visual learning and communication, where we have people in pedagogics, didactics, who are studying the phenomenon of how we learn using visual media. We do a lot of work on workflow situations in the group for media design, where we're looking at things like air traffic control environments, and in the information visualization group is now really soaring, because they're focusing a lot on explainable AI, and how we are looking at not only 3 dimensions, but millions of different dimensions in the parameter spaces. But as I said, one of the most rewarding things about the whole center is the fact that we have these 200,000 visitors coming through. And it's nice for a university professor in computer science to be able to say that, you know, I have several 100,000 visitors in my lab every year, and many of them are children. and that we are using visual media and interaction to provide immersive experiences, interactive exploration, the visual learning that we're seeing. And here are just a few snapshots of the environments where we have children coming in. And it's such a rewarding experience. And this is one of my main items when I communicate to other computer scientists. It's so amazing to be able to show, using visualization, showing your research and see how children can consume and understand many of the things that we think that they are just not there in terms of capability and capacity to receive that kind of information. Our dome theater, and I was sad to see in Vienna that the planetarium at the museum is currently being dismantled. And I will talk a little bit more about this towards the end of my presentation, how we are using this large-scale immersive facility to do interactive science communication, and how we are now constructing several dome theaters all over the country to spread to not only 200,000 visitors, but looking at 2 million visitors per year going through our environments. The fundamental thing that I wanted to explain to you and wanted to talk about and also get your comments on is this notion of shortcutting the distance between the researchers and the general public. The person on the left is one of my friends. His name is also Anders, and he's a medical doctor. He's a radiologist, and he's been doing research on how to retrieve data, how to visualize data, and I've been helping him for almost 30 years to develop tools and methods for doing medical visualization. What he's doing is exploratory visualization. He wants to explore, he wants to find items, he wants to identify the proper diagnostic work in the medical domain. What we realized when we started working with the science communication is that I can actually take the same data, and I can take the same computer, I can even take the same software and algorithms to produce interesting and engaging experiences in the public space to our visitors. This is what we traditionally call explanatory visualization, how we explain things. But there's an element of exploration in there as well. There's also an element of explanation in the research process itself. So we really felt the need to come up with a word that denoted this sort of confluence, the convergence of the notion of exploratory and explanatory. Thus the name Exploranation. And as I said, it's a complicated word. We'll see if it takes off, but it's the best thing that we could come up with in terms of explaining that we are both exploring and explaining at the same time, explaining and exploring, going back and forth in these loops. And pretty much everything that I'm going to talk about today has its origin in this idea that we are exploring and explaining, and that's sort of paving the way for a new generation of interactive experiences in the public spaces. So if you look at this confluence and the various research domains that have to converge, you're looking at the traditional science communication that we're lending a lot of ideas and practice from that domain. We're looking at the research on data visualization. We're looking at the research on interactivity. And in this intersection, in this Venn diagram, you find this notion of exploration. And I think this sort of explains why we have such a diverse set of people working in our environment, because we need to cover all these bases to make these things happen. There are some challenges, and I will be upfront with the challenges in Exploranation. You know, one of the first challenges is that we can produce some pretty nice looking images with the state-of-the-art graphics that we have, but we're dealing with the gaming generation, and these are kids that are spoiled in terms of the graphics, the quality of gaming, and I had experiences with kids coming up and saying, pushing on one of our equipment and, oh, it's lagging, it's bad graphics, and you just want to tell them, hey, it's actually 25, 30 gigabytes of scientific data you're rotating. It's not a game. So there's a challenge in terms of maintaining that quality and the notion of the realness of the data. Interaction is a problem. It has to be fast, accurate, robust, and multi-user. Everything that can break will break, and I know that some of you have experiences of perhaps interactive installations in public spaces. And one of the form factors that we have been relying a lot on is, of course, touch tables, because they lend themselves to that kind of multi-user situation, and the touch interaction is very robust. So you will see a few examples of this. The storytelling component is also important, that we actually do interesting storytelling, and that you find the items that you think are important in terms of actually reaching the learning goals. how do you make sure that children that come here as a part of a school program, that they actually reach the goals of learning that are specified in the syllabus? But do that in sort of an informative and captivating gamification setup that we're working with a lot. So these are the challenges, and it actually forms a full research agenda that we are working on. So many people over here. To refine this notion of exploration, we actually use the word for a new laboratory where we are really putting out the research prototypes. And we are providing these experiences. The globe that you're seeing here is a science on a sphere globe that you can interact with. And actually in the project that we're running right now, we're turning it into talking planets that you can actually walk up with the help of large language models. You can start talking to the planet and ask questions about how are you doing today and what's happening. And it can show you the ocean currents, global climate change, environment, pollution, 100 different data sets that you can talk to. So this is a very nice setup that we have. But I'm going to start off by showing you a few examples, so just to get the notion of the exploration process. You saw Anders Persson before, my friend, the radiologist. He has access to all sorts of medical scanners that you can ever imagine. And of course, that was a source of data that we used a few years back. And it's amazing. You get 25,000 image slices from one patient in about 2 seconds. And you put the patient on the table and you accelerate, and then you brake before the patient hits the wall on the other side of the scanner. That data in combination with the amazing development of graphics processing units. And sometimes I joke and I say, you know, the machine that I bought in 1999 when we started out here on campus, I paid about 600,000 euros. And it was a Silicon Graphics Onyx 2 Infinite Reality Monster machine that I bought. And that machine can today be replaced by an iPhone. And you know, these new NVIDIA GPUs that are coming out are just amazing piece of machinery. That and of course they're also used for artificial intelligence and machine learning at this point. But there was a long journey of you know, different research publications that we put out, primarily here, you know, showing some of the examples from the medical domain over the years, and these are actually also papers that are very close to what Torsten Möller is working on. So Torsten has been a collaborator and also a discussion partner in many of these projects here over the years. And this, we specialize in something called the transfer function and how we can use that to filter out the important components in this. So the state of the art today is what we call the correlated photon mapping that we have developed in terms of actually showering data sets with virtual photons that are bouncing around. And we can do that on time resolved data. But here's one of those scans. It's a woman. She had an aneurysm in the brain. And she was scanned, and all of a sudden we can do things like this by, you know, showering the virtual photons, so we can peel off the layers and look on the inside and find the little silver clip that was used to fix up her problem at this point. So she's still alive and doing well. But you know, one of the important things here, this for me, coming from my perspective, it's not only the visual. It's not only the application, the story about the medical, it's also the story on how. How did we make this happen? And the understanding that you need to do some math, you need to do some programming, you need to program that GPU. I don't expect people that come to us to actually understand this equation in its details, but I want them to know that it exists. I want them to know that for every single pixel on the screen, I'm solving this equation 60 times per second. And just that notion creates a little bit of the magic behind the exploration session, is that you understand that there are many, many different competencies that have contributed to making this happen. So what we did a few years ago was that we put that rendering algorithm and that equation, we put on a touch table. And we combined it with the multi-touch technology. We did some user interface design, and all of a sudden we had a new way of working with medical data. We're talking 2010 here now. So this is just when the iPhones are becoming popular and the iPads are coming out on the market. And we had this huge iPad that we got our hands on, and we did some work on that. And we put out a video on YouTube, and people were, wow, you can actually do this with medical data. You can interact with it in this way. And but instead of showing you a video, let me see if I can stress my computer's capabilities here and switch over to it usually crashes when I do this. We'll see if it actually works here. Okay, let me see. Yes, it's going to crash, but don't worry, it's going to come back again. So let's see. There we go. Bear with me for a second. Okay, so the first data set that I'm going to show you comes from a traffic accident. And this is a patient, and she died during very tragic circumstances. So I should say that it's always with the deepest respect for individuals, the families, and people that have died during tragic circumstances. But it's technically very interesting, and it's a good demonstration of one of the first data sets that we looked at. So I'm now running this on my laptop, and it has an NVIDIA 3090 GPU sitting inside. So it's getting pretty warm as I'm starting to rotate things around here. But what I can do with the magic of volumetric rendering is to just peel off the layers. So here comes the body. And I can rotate the body around, and just like it's the same data set. So now imagine there are about 7,000 slices of image data. And that data contains information about how much X-ray that has been absorbed in each of the points inside of the body. But what I can do now is, of course, just to change in that equation, I can just change the contribution from each of those sample points that I'm going through, and peel off layer after layer. And to cut to the chase, here you can see the bone structure, and up here you can see the primary fracture where the car hit this poor woman. You can also see that I'm doing storytelling, because here's an information tag. So I can get some information about this particular case, and I can get clues to what is it that I'm going to look at next. And of course, one of the things that I find in this particular data set is that there's a fracture up here on the jawbone. And if you find a fracture there on the jawbone, you think that something might have happened in the neck. So let's see. So I'm going to cut through the body like this, and here goes there goes the neck like this. So here you can see, here's the cause of death right over here. There's the broken neck right there. So this was the first case that we did, and we still use it as even though the data is not as high resolution as we have these days in other cases, we usually show it because it has an historical value for us. And it's also one of the few cases where we have the permission to actually show the data. We have done more than 10,000 virtual autopsies of real forensic cases. So every single case that comes in to the hospital here where they want to do a forensic autopsy, we also do a virtual autopsy. But just for the sake of argument, let me show you some other data sets while we're here. And here's one data set. This is actually my friend Anders that you saw before, and he's scanned himself in his own scanner. And here you can tell stories. You can tell so many different stories about different things that are so interesting and exciting. You can see here, these are the artifacts from the scanner, where you have missing data because of the filling in the teeth. And then you get this, what we call the streaking artifacts on the head here. And I'm going to be nice to Anders and turn him around this way when we peel off the clothes. So here we go. So you can see him from behind. I'm going to go to the skeleton. And here you can see one of those things that is also interesting to look at, to realize that it's X-ray. You can see the metal down here in the sole. And you know, when kids see this and they start interacting with it, when they figure out that the zipper in the jeans is hanging in the middle of the air here, they start laughing hysterically. Here you can see actually Anders didn't know that he had a pretty bad back, so there's some early stages of scoliosis here, and a bad disc over here, the signs of aging that we have here. So this is sort of the exploration and how you're completely free to look at things, and you can look at the gas distribution inside of the body if you want to do that as well, which is interesting. To avoid switching too many times between PowerPoint and the software here, let me just show you that we are also working with scanning all sorts of other artifacts together with museums. And this one is one of my favorite ones. It's a gecko lizard, and it comes from the Natural History Museum in London. It's a small piece of amber, and inside this small piece of amber, 20 million years ago, a gecko lizard got stuck in the tree sap, and it turned into amber, and it's sitting in there. If you look at this, it just looks like a regular amber stone, but we know the secrets what's inside. So what I can do now is just to peel off the layers again and start extracting out this 20 million year old lizard, long before there were humans on the planet. This one was alive and crawling around. But you can see the bone structure here. Everything is just collapsed inside of the amber. So why is it that I can see the skin? Well, here's another trick that I play with the mathematics, because what I can do is cut through the amber, look at it on the inside here, and you can see what we're actually doing. We're visualizing the imprint of the scales in the amber itself. Let's just flipping a sign in the equation, plus to minus, and then we can do the surface instead and extract the skin like this. So yeah, there are many, many more examples. Oh, I have to show you this one as well. Okay, yeah, now that it's in front of me. So this is a stingray, and again, this notion of the beauty of the data, the beauty of the things that we're showing, and the quality of the graphics is also very, very important. So let me peel off the layers and look at the muscles here. But when I saw this the first time, I was like, I want to print this one, because here, look at the skeleton of a stingray. And it's such an amazing piece of art that you see here. This is the wonder of nature that you're looking at this point, right? Okay, let me switch back to my presentation. So we got a lot of attention from this, and we got media, press. My wife said, "You're finally okay because they've written about you in The Economist." That's her measure of success. And we left a lot of those comments that came in. So, but what happened was two different things at the same time. We really started producing the medical visualization table, and I'm happy to say that in a commercial effort that we launched, we are now reaching out to more than 50 countries and training medical doctors. So anatomy classes are using our visualization technology to improve medical education in anatomy, but also in complicated cases for surgery, traffic traumas, everything like that. And there's been a huge demand for these tables, and we have 10,000 that have been shipped. But of course, we can't do it as a research group, so we're doing that together with a company called Xrays. But here is the other strand that happened at the same time. So this is the Swedish Crown Princess. I don't know how much you're into Swedish royalties, but this is the Swedish Crown Princess at the World Expo in Shanghai, when she actually saw this invention the first time, and she was thoroughly amazed by this. But we had thousands and thousands of visitors at the expo coming through that wanted to try out and look at the medical visualization table. And this really formed the starting point for another effort that has been going on for quite some time in terms of pushing this technology out into the museum. Here's the Natural History Museum in London, where you can look at the dissection of insects, for instance. But one of the more interesting installations that we have is the British Museum. And the British Museum has I think close to 8 million visitors per year at this point. And they have so many interesting artifacts and subjects. Here's one of the ones that they're most proud of, which is the Gecko man, a 5,500-year-old mummy, and he's been at the museum for more than 100 years at this point, and no one really knew the cause of death for the Gecko man. So we transported the mummy to one of the hospitals in London. And we did an X-ray, a computer tomography scan of the mummy. And here's the first session when we have Neil Spencer, who's the keeper of Egyptology at the museum, and Daniel Antoine, he's the Physical Anthropologist, Head of Human Remains. It's an amazing title. And this is the first time they actually look at the mummy on the inside. So what I'm going to do is actually, thanks to the British Museum, show you the Gecko mummy. And let's see if we can get out there and do that. Okay, so here we are. So here's the Gecko man, and volumetrically rendered, about 10,000 slices of image data. And Daniel and his friends, they have been looking at Gecko man for many, many years. You know, he was his natural mummification, so he wasn't mummified like they did in later years in Egypt. He was found in the sand close to the border to Sudan, close to the place of Gecko. And they've been at the museum looking at him and trying to figure out. They know that he's a young male, but they were also curious, what was the cause of death? So they've been looking at this sort of fold on the back here and thinking, is that this just the way that he ended up lying and the skin dried that way, or did something happen back here? And of course, Anders Persson, our radiologist, after we did the first scan, just did a virtual autopsy. And what he found immediately was, of course, what you're going to see now, which is the broken rib cage on the inside here. So the Gecko man was actually murdered. He was stabbed in the back with a knife, and that knife fractured the rib cage and punctured the lung, and then he was left in the sand to die. We actually even found a knife that would match that wound. So we can say that we found a 5,500-year-old murder case, and we found a murder weapon. But of course, we did not find a murderer at this point. So here he is, and again, we can peel off the layers. It's very hard to visualize mummies because the X-ray absorption in dried human tissue is about the same. But you know, with the help of our transfer function settings, we can do a decent job of filtering out some of the things. And we can, of course, look at the skeleton. You can see one of the things, if we look at the original thing here, you can see that if I cut from above, you can see there's the brain, which is sort of, you know, it's shrunk and dried up, and you can see dried human tissue on the inside of the body like this, if you peel off the layers. So why am I showing you this? Well, I think there's a story behind this that's important to tell. And it's not only the story that media, because, you know, it was kind of funny to see that they wrote about murder at the British Museum, but they didn't say there was 5,500 years ago. So, but what I think is important here, and what I wanted to talk to you about, is the design principles behind these kinds of installations and how we are simplifying things. And these are sort of the 5 mantras that we're applying there. We all the time, we want to have an object focus, that you never lose the immersion and the notion of actually touching something that is real. The interaction has to be very constrained when you look at the global perspective, but when you go into the micro level, we are releasing that freedom. Very small icons, keep the interface as clean as possible. And of course, the multi-user interaction has to be limited, because if you had too many people interacting with the mummy at the same time, it's problematic. Also, these presets, of course, there's a lot of mathematics that's hidden behind when we can peel off these layers. If I bring up the full interface to also tweak the parameters in that equation that I showed you, it's going to be very complicated. So we need to hide that away from the user, but still retaining the notion of being free to explore and experiment with the settings of the visualization. And of course, the narrative in terms of the information tags that we have, that gives you contextualized information, but also hints to further exploration that you may want to do. And of course, they have to be multilingual and user adaptable as well. Here's perhaps a slide with too many figures and numbers on it, but I think it's a very, very important slide, because when you work with museum curators and you start talking about digital installations and digital artifacts, they go, oh, no, it's going to take away attention from the real object or the real subject that we're looking at. So we had a person sitting in the gallery for 6 months and looking at the studying the visitor flow through Gallery 64 at the British Museum. And here are just some of those key numbers that I think are important to look at. After we introduced a touch table with the Gecko mummy in Gallery 64, the dwell time in that gallery increased by 40%. So people spend 40% longer time in the gallery. During opening hours, someone was interacting with our touch table 95% of the time. The fraction of visitors, if you look up on the right-hand side, the fraction of visitors that actually stopped and viewed the physical display increased from 59 to 83%. So in sharp contrast to what people are afraid of, the number of people who actually look at the real mummy increased because they had also looked at the digital installation. And up to 60% of the users of the touch table discovered the cause of death. So they were extremely happy, and therefore it was turned into a permanent installation. And if you go to the British Museum today, more than 5 years after this, 6 years after this, then you will still see that installation there. And if you want to read more about it, you can look up this reference here, Communications of the ACM, where we describe the whole process and how we work with the museum and how we made those renderings that you have seen some of them here. And here's the Ynnerman photon mapped with Daniel Jönsson, who's my former graduate student, and his framework for doing photon mapping of volumetric data. But you know, the most important thing, and I think this is something that we really need to push out there, is that if you do these things, it's such a rewarding experience for a researcher like myself to actually go to museums and see how children are being interested in, how they're being engaged, how their curiosity and their exploration is supported by some of the things that we're doing. And for me, as an individual researcher, this is so much more important than writing research papers, which of course is important too. But this is a really rewarding exercise to go through, and I think we need more people over the world who are engaging in this domain. I don't know if I have time to show you this, but yes, I do. I will just take a minute because I really wanted to show you some of the latest, coolest stuff that we have. So what happens if we go beyond medical CT? And I'm not going to talk about synchrotron radiation too much, but you know, it's X-rays with 100 times higher resolution than what we have in the regular domains. Let me just show you that. It's such a cool thing. Let me see if I can do that. Okay, here. Okay, and then again, I have to exit out of this application here and relaunch it because it's another piece of software that I need to fire up for you here. Thanks to our little spin-off company that's taken over some of these things, that we are getting more and more data. And here I want to show you. This is the biggest brain in the world. We're bragging a little bit here, but this is a 69-year-old female, and it's from the ESRF, the European Synchrotron in Grenoble, where we got this data from, and I'm going to explore that brain for you. It takes a while to actually process some of the data because we're now building a multi-resolution structure. And as you will see in a minute, there's a lot of data that we need to process to get the brain up on screen. So bear with me. And as I said, my machine is getting pretty warm at this point. So here's the brain. I can zoom in on it, and again I have the same sort of setup with the storytelling items, and again I can change the color. I can look at the white matter in the brain if I want to, and peel things off if I want to. So let me go to the first high resolution scan area. It's right down here. I don't have we have access to the full brain at high resolution, but we're just taking a cylinder here. So and let me cut through that cylinder a little bit here. There, you can see them. And I'm going to zoom in on this particular part of the brain there. So this is the next level down, and you're beginning to see some of the fine structure in the brain. And I'm going to take away all the context around it. So here we are. So there's that cylinder of brain tissue that you're looking at. Now, what I'm going to do is look at the blood vessels inside of it here. So these are, the fine structure and the brain. And here I have even higher resolution in the scan area down here. So let me look at that and zoom in. Now you're down to the neural level. Right? And when you look at the neural level, you're beginning to see the fine structure of the brain. So here it is. and you look at the blood vessels. These are the blood vessels that are providing blood to individual neurons inside of your brain. And that's pretty cool to look at. And if you want to talk about neural networks and artificial intelligence, we're still at least an order of magnitude away from reaching this level in the machine learning algorithms that we have at this point. All right. I just wanted to show you that. But what is it that we have done? Well, we have looked at representations, abstractions, and we've looked at the combination of visual language, cognition, how we make that rotate around to make sense out of this, how we construct the knowledge and how we are rotating around in this. And that visualization is really the engine that makes many of these processes happen. And there's a paper by Konrad Schönborn, who is our professor in pedagogics and didactics here in visual learning and communication, that describes all of these individual components in the sort of the journey through the data exploration that we have identified in our setup. You know, you look at this machine learning and all of these efforts that are going on and inspired by the brain. And I just put this in here because I wanted to show you some of the things that we are doing at this point. And I'm sure that you have tried out things like ChatGPT and DALL-E and all of those methods that are out there now. Generative AI is a big thing. But what we are doing now is that we are looking at transferring some of the notion of the guide into a large language model. And don't be too upset with us for doing that. It's intended to be a complement to the real physical interaction with a human that you might have. But we're doing this together with some of the providers of interfaces like the big company NVIDIA that is really supporting us in doing this. And here's actually the CEO of NVIDIA. I don't know if you're following the stock market, but you may have seen that the NVIDIA release of new hardware yesterday turned this man next to me into one of the richest people in the world at this point, which is amazing. But our goal here is to look at pushing the limits of technology so that you can have an engaging experience. And here's actually a survivor of the Holocaust, and it's a few years ago that we did this together with Paul Debevec, who was the head of the Institute for Creative Technologies in California, and one of my professors here was over there and helped out with the design of this holographic display that was used to provide a query answer system so that you can actually sit down and have a dialogue with one of the survivors of the Holocaust. And this is, of course, one of the important missions is to document. And we're doing similar work now with the Apollo astronauts that went to the moon, and there are 4 of them that are still alive at this point. So we're looking at various ways of transferring the knowledge into the virtual space as well, and also have that guided experience. My last part of the presentation is going to be about the Wolstone Project, and I haven't said much about the dome theater that we have, but it's a really nice environment to work in, and I wish that we could just be sitting in the dome, all of us, and we could show you some of the work that we have been doing. And of course, we are now spreading that work to other places in Sweden. So Sweden is going to be the most dome dense country in the world per capita, because we're building one far up in the north in Umeå, we're building one in Stockholm, we're building one in Gothenburg, and one down south in Malmö. And they're very spectacular, each in their own way, and they're all opening up this year. So we will be touring with our content all over the country and reach the goal of, instead of 200,000, about 2 million or maybe even 3 million people visiting our domes. And here's some shots of the construction that's going on as we speak. What are we showing in these domes? Well, one of the pieces of software that we have is called OpenSpace, and OpenSpace is an interactive piece of software that makes it possible to fly through the universe from the microscopic scale down on Earth all the way out to the Big Bang, and you're free to fly wherever you go. And we do shows on this, and we have a pilot, and we have a narrator, and it's fun to have people just shout out in the room where they want to fly, and we go there and we look at things like the Martian surface. Another show that we have produced is called Making Magic. It's a visual effects story, and when we made this production for the dome, the people there said, well, we only have one requirement on this production. There has to be a dinosaur in it. So I used the dinosaur as the carrier of the story that I wanted to tell. the story about mathematics, the story about physics, the story about programming, the story about design, art, and storytelling, that you need to have all of these components if you are going to make a dinosaur in the visual effects or in the computing gaming industry. And I think that message really comes across in a very, very strong way. And if you look at the dinosaur, it jumps out in full 3D stereoscopic viewing and bites you in the head towards the end. But you know that it's math, you know that's programming, but the illusion is still there for you. So if you come here, I'll scare the pants off you in our dome theater and have a dinosaur bite you in the head. We have one production on AI that we're working on at this point, how to communicate what AI is really about. And you know that there's a lot of discussions in media at this point. So we want to give a sane view of AI and educate people on what are the limitations, what are the potential risks, and also what are the benefits to mankind of AI. And one that we have just finished now is called Chemistry of Life. And I wanted to dwell a little bit on the chemistry of life because this is something that we have been doing together with Drew Berry, who is the famous animator from Australia, and also some people, as you can see, from Vienna, Ivan Viola, who's now down in Saudi Arabia, and Tobias Klein, and Peter Meindek, but Eddie Gröller, who is in Vienna, not at the University of Vienna, but the Technical University of Vienna. The focus of this production is as I said, the chemistry of life. So it's really is the fundamental biological processes. And just to give you a little bit of a flavor, this is what it looks like. So this is inside of the mitochondria. And we're telling the story with the help of Drew Berry's amazing animations. We're telling the story of how the biochemistry works inside. And this is called the ATP synthase, the yellow molecules that are coming out of that are called ATP, adenosine triphosphate. And we are producing billions and billions of those per second. Actually, you have 10 grams of ATP in your body right now, and the body consumes about 1 gram per second. Every single living life form on our planet shares this fundamental process. And so just by looking at it, and if you bring that to a setup like the Dome Theater, the challenge in doing that is to render that process in 360 degrees in 120 frames per second, 8K resolution, stereoscopic viewing. And when you're sitting there and the ATP is flying through your hair, you get really engaged and immersed in this fundamental process of life that you're seeing in front of you. And also as a science communication aspect of this is that, you know, we're touring the world. This is in Montreal when we had a pre-screening of the chemistry of life, and I and Måns Larsson, who's the animator behind many of these things. This is a dome theater where you're actually lying down on your back, so they're on bean bags, the whole audience, and appreciating the actually being immersed inside of the biomolecular world of the mitochondria. So it was a bad dome theater because the projectors were peeking through the holes there, so the blinking light is actually a projection light. Okay, I think I'm actually in this to save some time. I'm actually going to skip this part, and I don't know, Torsten, do I have another 5 minutes, or what's the timeline?
Sure.
Another 5 minutes. All right. Okay.
Yeah.
All right. Okay. Then I'll just show you the Corona exhibition, so what we have done here is to actually another one of these touch table stories that I want to wrap up with, and again it's together with Nanographics, sort of a company based in Vienna, and some other collaborative partners, the SciLife Lab in Stockholm as well. So what I'm going to do is again bring up, if my piece of software still supports me, I'll bring up another version of the software. Here we go. There we go. So here's the coronavirus. And what we really wanted to do here, that was during the pandemic that we did this. We wanted to tell a story, and to tell a story about the coronavirus. So here's the virus itself, and And again, you can cut through the virus, you can look at it on the inside, you can learn about the virus and the envelope proteins, you can look at the spike proteins and all of these things. But just to save some time, let me continue and say, okay, here's the notion of the virus. What is it about the virus that makes it so unique? Well, it's the spike protein. So here's the story about the spike protein with the cryo-EM data, which is the highest resolution scan of that particular protein that's been modeled that way. And what I can do now is to look at the various active parts, the various parts of the protein, and see how they are working together. This is the intense research on why this spike protein is capable of opening up the membranes on human cells so efficiently. So you can learn about the virus, but what I wanted to do with the help of my colleagues at the Interspectral was to tell a story about a full patient. So if you get exposed to that virus, what happens to you? And this is where the story gets a little bit difficult. And again, when we're showing cases of individuals, it's always with respect for them and also other people who have suffered from similar disease problems, but I think it's important to communicate these things. So here's a patient, a 70-year-old male, and here we have a scan of the body and the lung before the pandemic. Relatively healthy person, not completely, but relatively. So this is what the lung looks like when you cut through. In May in 2020, he contracted COVID. And the scan was made, and we have co-registered that scan. So here you can see the onset, the beginning of fluid accumulation and inflammation in the lung. So here's some pretty bad cold symptoms at this point. Just 3 days later, on the 12th of May, he develops full COVID. And here's that viral storm inside of the brain, and you can see how severely affected the lung is by the COVID virus. So here's getting oxygen, and at that point, it's decided that we really have to do something about it. So he gets put under and he gets intubated. And here, this is the 5th of June, a month later. And you can see there's almost zero lung capacity at this point. And then we take another scan 1 month later on the 1st of July. And now he's full tracheometry down here. And you can see that the lung is actually beginning to recover slightly. Unfortunately, for this particular patient and individual, he recovered from the COVID situation, but unfortunately died of complications a few months later. So, but we do have the permission to show his data here online. But of course, also what we did, now you have the perspective of the virus, the protein, and the human body response to that virus, and also here's the global response to it. So we put together a crude visualization of the timeline of the virus and the first cases, the first lockdown in China, for instance. And then you can scroll through and you can read about the various events that happened all over the world, all the way to the 31st of December 2020. Right. So just to wrap up, I think what we have is some sort of new science communication paradigm. I don't claim that we are the only ones that have discovered this or doing this, but we are perhaps the ones that are pushing the forefront in terms of bridging the gap between the research in computer science and visualization and science communication. And so we're taking these research results, we use them for public engagement, and that actually also promotes the visualization research in itself. So just to show you the benefit and how rewarding it is to work here. I mean, you get comments, you get support, you get satisfaction, you get research tools if you're a domain expert, but you also, as a research in visualization, you get access to data that you otherwise wouldn't get. You get insights and you get lots of explanations and reflections on the work that you're doing. And in the middle of this is all these things like the visual metaphors, the interaction paradigms, the authoring and storytelling tools, and the software frameworks that we need to develop. Now, the stuff that I've shown you over the past hour is, of course, not only my own work. It's based on contributions from many people and also organizations like the Medical Center over at the University Hospital in Linköping, Interspectral, a spin-off company, the people at Sectra, another company, and there's a large number of very, very brilliant, smart people who have been contributing to this. And our partners, such as the American Museum of Natural History, in particular, when we're looking at the space-related work that we're doing. So with that, I would just like to say thank you for listening and take any questions that you might have online.
Thank you very much for a lovely talk. The floor is open for questions. And yeah, anyone wants to go first? João?
I am sorry that I jumped into the queue without. First of all, hi, Anders.
Hi, João.
This was an amazing and very inspiring talk. I knew about open space, and I realize now open space is about 1% of what you do. I'm speechless, and it is a great pleasure to see you here. I hope we meet again. I have teaching starting in 2 minutes, but I wanted to say hi to you.
I'd love to connect more about open space and the possibilities and the latest stuff that we have been doing there now. A lot of things are taking off in that domain.
I would love to hear more. I should visit, or you should visit.
It would be great. You're always welcome. Yeah.
Bye-bye.
Bye.
Sophie?
Yes, thank you so much. Alice, thank you so much for this presentation. This was absolutely fascinating. I hope you don't mind me asking a question. I mean, I'm a social scientist, so not an expert at all in the technicalities or in the kind of technology that stands behind all this. So I have absolutely no question about that. But from a social scientist perspective, I have 2 questions, and because they connect very much to my research also on visual communication. And everything you present is just fascinating. I mean, from a human point of view, as a human watching it, but also from a scientific point of view. And the first question I wanted to ask is, you said somewhere at the beginning of the talk that it's important for you that people understand what's the technology, the maths that stands behind all this, and that you've also tried to explain it or like contextualize what is the work that stands behind all these visualizations. And I was wondering why this matters to you. So is this more like on a meta level that you're thinking it's also part of science communication to explain the scientific method, so to say, that stands behind it? Or is there another motivation? And then the second question connected to that, I saw that you've shown like how people interact with these exhibitions and with these tables and everything, and that people dwell more and interact more. But did you also conduct research or in combination with others or in collaboration with others about what the actual effects are on individuals? So learning, kids or grown-ups learning about science or knowing facts, or also on a more like organizational level, is there like a higher correct way of identifying certain injuries or forensic effect that we can see? So I wonder what type of research you've done on that. Thank you.
Sure. Let me start with the first question. And of course, there is a motivation why we're doing this. And the big motivation lies in STEM or STEAM. That we have a huge problem in the Western world with the interest that's going down, decreasing interest in science, technology, engineering, mathematics, and arts, right? So if you measure the interest in those topics in the 3rd grade in Sweden, and I think it's the same in Austria. If you look at, it's pretty high interest. People are very curious. The kids are curious about math. They want to know about natural science. They want to know about things, right? They're very curious. Then you measure the same level of interest in the 9th grade, and the interest has dropped dramatically for the boys. It's gone down quite significantly, and for the girls, it's gone. No interest. So something traumatic and dramatic happens to kids between 3rd grade and 9th grade. And for us, our mission is to use the interest that people have in the applications, showing why is mathematics good for you? Why is it interesting? How can I use it? Because we're so bad at that in the schools, to show that, yes, you can be interested in math because it's interesting in itself. But if you put a little extra effort into it, then you can actually accomplish some really amazing things in the medical domain, in space domain, in engineering, and we need to get much better at showing that. And visualization is the perfect tool for that, so that you can engage and raise the interest in these topics. So that's of course the motivation why we are doing this primarily. Looking at the documentation of the research efforts, just Google Konrad Schönborn or Google me, and you will find lots of papers that are describing from a visual learning and from a didactics research perspective, how we are measuring the engagement, the role of the visual metaphor, and the scaffolding that we need to apply, and how we build those things, and what works and what does not work in many of those contexts. There's a bunch of papers on this. And if you're interested, I can put you in contact with Konrad as well, because he would be the person to talk to about many of these things. Now, what was your third question? Oh
no, I think that was it already. I mean,
right. Okay.
If I may just add, because we've done a lot of research in communication science about, well, not a lot, but some research on immersive journalism. So this idea that, you know, journalistic news organizations try to use visualizations and VR and AR and whatever, trying to get people engaged again in being interested in the news and politics. And there's mixed experiences with that, right? So this idea that people enjoy visualizations but don't necessarily get more interested in politics from them.
Right.
So there's like a discrepancy in like what the technology can actually do, or like what type of attitudes can it actually change, right? It can change, it can intention definitely, but also, for example, political interest, or as you said, interest in maps. And for that, I'd just be super interested to have these more long-term views. And I know this type of data is very hard to come by, like over life courses. How do people's interest in maths or interest in politics change when they're exposed to these types of visualizations? I think that's fascinating.
Absolutely. And, you know, these days, I mean, the debate right now, I mean, how can we not only measure the engagement, but also the ability to develop critical thinking? Because, you know, that turns out to be one of the main aspects now, in particular, if you're looking at the rapid development of AI systems and, you know, and the deep fakes that we have. I mean, the critical thinking is becoming such an essential component in the skill set for the next generation.
Thank you. Thank you so much.
Yeah.
Thanks. Any other questions? Maybe I have a provocative one in the sense of when are you expanding your domes beyond Sweden, like Austria or something?
Well, you just closed down the one you had, so. But we would be happy to, if anyone has an initiative to and want to raise the funding and use us as an example, we're happy to contribute, and content-wise, of course, as well. Yeah.
Okay. Are there any other questions?
But you're welcome to come visit, and I'd love to, Sophie, I'd love to discuss more about your perspectives, and maybe there's room for some sort of collaboration there. Yeah.
That'd be amazing. Yes, thank you.
Yes.
I think I have a question which is a little bit more out of the box. I'm not a computer scientist, so I grew up with literary studies. So thank you, first of all, for making your presentation so understanding for normal people. Thank you. That was very interesting. And when you were talking about your domes, I couldn't help but think about the Abba Arena that they built in London. And I think so basically I'm just asking, is it kind of a similar technology behind that?
Both yes and no. I mean, the Abba Arena is based on something called the Pepper's Ghost, when you actually have it's actually flat videos that are being produced, but they're being reflected on a semi-transparent mirror, and it fools the human eye. So it's more like a perception trick they're playing with you. So it's not fully 3D holographic viewing that you have. And this is a technology that it's called Pepper's Ghost because it came from the theaters in London in the 1800s, when they wanted to have ghost characters on the stage, and they put the actors under the stage, and then they illuminated them, and then they were reflected up on the semi-transparent mirror. and that's why it's called. So it's an interesting phenomenon, and it's being reused. And the first time I think it was used in a large modern public space was the revival of Tupac. I don't know if you've seen that. You may be too young for that, but he was killed back in the 90s, I believe, and he was revived virtually on stage, and people were like, "Wow, how did this happen?" It's like 3D, and it's like, no, it's a video, but we perceive it as 3D. Yeah.
Oh wow! Thank you. That was very interesting.
Yeah.
Right. Anybody else? Because if not, we extended our time already. It was fascinating to listen to you, and I really appreciate your time. And so thanks again, and thanks everyone for attending. Greetings to Sweden and also to your family.
Yeah, thank you so much. I'm looking forward to the next visit to Vienna. As some of you know, I was there back in January, and I'm looking forward to my next visit. And if anyone wants to schedule discussions, now that you've heard a little bit about what we're doing, I'd be happy to meet up with any of you.
That's great.
Thank you so much. I will definitely get in touch. Thank you. Thank you, Anders.
Thanks so much. Have a good weekend, all of you.
Thank you, everyone.
Have a good one. Bye-bye.